Amplification of modulated waves in magnetoactive semiconductor plasmas. Abstract using the hydrodynamic model of semiconductor plasmas and considering the origin of plasmon-longitudinal optical phonon interaction in effective third-order optical susceptibility, an analytical investigation of amplification of modulated waves is performed in magnetoactive semiconductor plasmas. Expressions for necessary threshold pump amplitude for the onset of amplification of modulated waves and growth rate of modulated wave have been obtained. Numerical estimations have been made for n-InSb crystal at 77K illuminated by a 10.6 m CO2 laser. The dependence of threshold pump amplitude and growth rate of modulated wave on wave number, externally applied magnetic field, via electron-cyclotron frequency, and doping concentration, via electron-plasma frequency, have been explored. It has been found that the threshold pump amplitude can be lowered whereas the growth rate of modulated wave can be enhanced by proper selection of externally applied magnetic field and doping concentration of semiconductor medium. The results of the present analytical investigation strongly manifest the importance of magnetoactive semiconductor plasmas as appropriate hosts for modulational instability processes. Keywords: modulational amplification, Freilich interaction, threshold pump amplitude, growth rate, semiconductor plasmas. Introduction. Laser semiconductor plasma interactions have been playing a prominent role in diverse areas of scientific research for several decades due to its immense applications in processing of materials and fabrication of devices. 1, 2. Semiconductor plasmas also provide a compact and less expansive medium to model nonlinear optical phenomena encountered in laser technology. There exist a number of nonlinear interactions. The modulational interaction of coupled modes is significant one. In modulational interaction, a strong space charge field modulates the pump wave. 3. Periodic variations of the propagation parameter lead to the modulation of an electromagnetic wave passing through the medium. The optical waves present in an electro-optic modulator can be strongly amplified through nonlinear optical pumping. The resulting amplification of decay channels by modulational interactions are generally referred to as an instability of wave propagating in nonlinear dispersive medium such that the steady state becomes unstable and evolves into a temporally modulated state. 4. Modulational instabilities have played a very prominent role in diverse areas of scientific research. The devices based on modulational instability in semiconductor plasmas occupy a special place in nonlinear optical technology due to their prospective applications in fast optical communication and optoelectronic devices. This is due to the fact that semiconductor crystals are substantially transparent for photon energies much less than the band gap energies and undergo optical damage at considerably large excitation intensities. In addition, semiconductors have added advantages over other materials in terms of compactness, control over the material relaxation times, observed large nonlinearities in optical properties under near-resonant laser irradiation and sophisticated fabrication technology. 5. In semiconductor plasmas, the pump electric field interacts with both electrons as well as optical phonons, OPs. As a result of this interaction, the scattered radiation consists of two parts. Single particle scattering, which is caused by individually moving electrons and is nearly elastic. This part of the spectrum can be used to determine the electron velocity distribution, and represents a great interest in transport theory. Collective mode of scattering, which is caused by electron-plasma wave, i.e. plasmon, PL, mode in the electron gas. In weakly polar semiconductor plasmas, the collective modes are strongly coupled with the longitudinal optical phonon, LOP, mode via Freilich interaction, and one observes a frequency shift with increasing free carrier concentration. 6. The coupling of LOPs and free carrier collective excitations by macroscopic longitudinal electric fields in a polar semiconductor has been treated theoretically by Kaplan et al. 7. This coupled wave approach can also be generalized to include waves other than electromagnetic. However, in centrosymmetric crystals, one may replace the idler electromagnetic wave by an optically excited coherent collective mode such as the acoustical phonon mode, OP mode, polaron mode, and polariton mode, etc. A polaron is a quasi-particle that arises due to the conduction electron, or hole, together with its self-induced polarization in an ionic crystal or in a polar semiconductor 8, 9. Here, it should be worth pointing out that Freilich interaction remains absent in covalent materials such as Ge and Si, but it significantly affects the mobility of weakly polar IIIV semiconductors. For this type of studies, IIIV semiconductors happens to be obvious choice because of the possibility of rendering them p-type or n-type conductors through doping. At low doping levels, the interaction remains unscreened. With increasing doping levels, PLS and LOPs will no longer remain decoupled, rather the system will exhibit oscillations at coupled PL-LOP modes with frequency, where P equals N0E2/M, 1/2 is the electron-plasma frequency and is the dielectric constant, in which is the high depletion of energy from the pump wave is being neglected. Semiconductor plasma is assumed to be homogeneous, possessing isotropic non-degenerate parabolic band structure at moderately low temperature, 77 K. 0. Frequency dielectric constant of the medium and 0 is the pump photon energy is taken well below the band gap. Permittivity of free space. LOP and top represent the LOP mode frequency and transverse optical phonon, top, frequency, respectively. M is the effective mass of an electron of charge E. Hence, it would be interesting to find out the doping levels favorable for PL-LOP coupling in a degenerate polar semiconductor plasma. Since IIIV semiconductor plasmas have been regarded as universally recognized nonlinear optical media with high optical nonlinearities which can be easily controlled by the application of external fields 10 to 12. In the presence of externally applied magnetic field, the collective cyclotron excitations LOPs coupling, via the macroscopic longitudinal electric field give rise to modified normal modes, i.e. polaron mode. Under Voigt geometry, polaron mode frequency at the center of Brillouin zone, 0 wave vector mode, is given by 13. Energy of the sample, it allows the optical properties of the sample to be influenced considerably by free carriers and keeps it unaffected by the photo-induced interband transition mechanisms. Finally, numerical estimations have been made with a set of data appropriate for a polar semiconductor plasma, n-InSb, duly irradiated by a frequency-doubled CO2 laser to establish the validity of the present work. Theoretical formulations. In order to study the PL-LOP interaction-based amplification of modulated waves in a magnetoactive semiconductor plasmas, the hydrodynamic model of homogeneous semiconductor plasma of infinite extent is considered. This model proves to be suitable for the present study as it simplifies our analysis, without any loss of significant information, by replacing the streaming electrons with an electron fluid described by a few macroscopic parameters like average carrier density, average velocity, etc. However, it restricts our analysis to be valid only in the limit KL. 1. K is the wave number and L is the carrier mean free path, where C equals E/M, B0 represent electron-cyclotron frequency in the presence of magnetostatic field B0. It is clear that presence of magnetoplasma excitations modifies the coupling of PL-LOP quite distinctively. Literature survey reveals that up to now, a lot of theoretical work on the amplification of modulated waves induced by coherent collective modes in IIIV semiconductor plasmas has. We consider the propagation of a spatially uniform pump wave E0x E0exp, I0t, in a weakly polar semiconductor plasma medium subjected to a static magnetic field B0 Here, the incident pump wave is assumed spatially uniform. K00, because under dipole approximation the excited waves have wavelengths very small in comparison to the scale. Been reported by several research groups 14 to 20, but PL-LOP interaction-based amplification of modulated waves in weakly polar magnetoactive semiconductor plasmas has yet to be studied. Thus, the aim of the present paper is just to investigate length of the pump field variation 21, i.e. may be neglected. K0K. So that K0. The amplification of modulated waves in magnetoactive semiconductor plasmas in the framework of a hydrodynamic The physics of the problem can be explained as follows: in the presence of two mutually perpendicular fields, E, B, the 0, model and coupled mode theory. We choose the weakly polar IIIV semiconductor crystal, viz. n-InSb as a model substance to have a polar OP scattering mechanism, so that coherent polar-on mode may be excited through ultra-fast excitation. An analytical investigation of the modulational interaction between the CO propagating pump. Motion of each free electron generates a macroscopic depolarization field normal to the surface of the crystal. The induced depolarization field strongly couples the longitudinal and transverse degrees of freedom of the medium and shifts the natural frequency away from the cyclotron frequency, and hence induces the collective cyclotron excitation with the beam and the internally generated polar-on mode, due to the resonance frequency 221/2. In the presence of coupling of PLS and LOPS, is presented in a magnetoactive semiconductor medium, as a result of which it is found that the polar-on mode is amplified at the expense of the pump wave. Further, by using coupled mode approach, strong tunable electromagnetic sidebands may be achieved as a signal waves at the expense of the pump wave. Nonetheless, the present analytical investigation has been made under the following assumptions. Pump wave. This collective cyclotron excitation generates a polar-on mode via Freilich interaction, between PL and LOP modes. This interaction induces a very strong space charge field and derives the polar-on mode at modulated frequency. Thus the pump wave and polar-on mode in the medium can be strongly amplified through nonlinear optical pumping. The basic equations employed in the present analysis are transfer equations of the oscillatory electron fluid and lattice ions, respectively. E and pH represent the electron-electron, known as momentum and energy conservation relations, collision frequency and the OP decay constant, respectively. These loss parameters have been introduced, respectively, under spatially uniform laser irradiations K00, phenomenologically and do not vary with the pump and the externally applied magnetic fields. S equals U plus U, is the relative displacement of positive and negative ions. These equations are similar to the PLOP coupled mode equations 22. The induced collective cyclotron vibration produces a polarization Pe equals Na. The induced variations also influence the oppositely charged ions of a diatomic crystal for the oscillations, and finally the oscillations result in an induced polarization Ps equals NQSS of the medium. The effective charge of the lattice polarization is given by so that K0 K say. Physically the polaron is an electron in a localized state that induces a polarization of the medium. This polarization is local in character and is due to the displacements of ions from the equilibrium positions caused by the field produced by the electron density, which gives rise to an electron density perturbation at the polar-on mode frequency, which couples nonlinearity with the pump wave and derives the polar-on mode at the modulated frequency. Following the procedure adopted by Singh et al. 24 and using x 3 and 6, we obtain, where m is the reduced mass of diatomic molecule and n equals A3, is the number of unit cells per unit volume, A being the lattice constant of the crystal. We assume that the electric fields associated with the electronic and lattice polarizations are where parallel to each other and the polarizabilities of the electrons and ion systems are additive. Thus, the simultaneous excitation of collective cyclotron vibrations and ops result into coupling between them. The resulting coupled vibrations appear in the form of a new mode known as polar-on mode. The equation of motion of a polar-on mode is given by 3-2 Pol 2 0 Pol 4-2 Pol C 1 NEQ 2 NE 2 R RE Q W 2 Q 1 SSS 0 2 R2 nm, 1/2. Constant, and n equals n0 plus n1 expi, kRt. E-pole is the effective electrostatic field associated with polaron mode. Let us consider that the motion of polaron mode takes place with respect to a new origin shifted by some distance from the original position. Under this assumption, we may express the displacement of polaron mode in terms of new parameter r, defined as r, nm, 1/2w23. In deriving EQ, 9, we considered only the resonant sideband frequencies, 0 pol, by assuming a long interaction path, i.e. semiconductor plasma of infinite extent, so that the higher order scattering terms, being off-resonant, may be safely neglected. 25, and the only waves coupled by the polaron mode are the incident, 0, and scattered wave at 0 pol. Using EQ, 9, these sidebands or forced waves can be expressed as other basic equations governing the said modulational. EQ, 7, is the continuity equation, in which n0 and n1 are the equilibrium and perturbed electron densities, respectively. V0 and V1 are the oscillatory fluid velocities of the electrons. EQ, 8, is the Poisson's equation, which determines the effective electrostatic field E-pole associated with polaron mode arising due to the induced electronic and lattice polarizations. We also assume that the energy transfer between the pump wave 0 pol represent the frequencies corresponding to upper and lower side bands, respectively. In deriving x 10a, b, we further assumed that the electron density perturbations at sideband frequencies n1, k, vary as expi, kxt. X 10a, b, reveals that the sideband waves are coupled to the polaron mode via density perturbation under the influence of strong pump field. It is also evident from above expressions the induced third-order polarization due to cubic that depend upon the magnitude of the pump. Nonlinearities at the modulated frequencies may be amplitude, via E. The density perturbations thus produced at the sideband frequencies affect the propagation characteristics, defined as 2 p 3 ee 17 of the generated waves, which can be examined by employing the general electromagnetic wave equation. The induced nonlinear current densities for the upper and lower sidebands are given by E0 pol. The use of x 15 in 17 yields the effective third-order optical susceptibility in the coupled mode scheme as 2K2 E/m 22 Z 1 242 J N V 11A 3 1 P12342 E 18 10 E 22 2 0 C and E. It is evident from EQ 18 that 3 is a complex quantity. 1 0 0 EEREI J N V star 11B, and can thus be separated into real and imaginary parts as the time integral of the nonlinear current density J 3 I 3 19A yield the induced polarization frequencies as P at the modulating, where 2K2 E/m 222 242 2 Z 1 P J dt 12 3 1 PQ124 E pol 0 pol 2 ER 2 242 2 The effective nonlinear polarization of the modulated wave is obtained by P 13 and pol 0 pol 0 C 19B 4K2, E/M, 222, 242, Z, 1. EI. Here, it should be pointing out that for the amplification of 3, 1. PQ Pol 124. E2. The modulated waves, both the side bands should contribute 242, 222 equally, and this modulation is then transferred to the polaron mode, which in turn, gets amplified. Thus from X 10 Pol 0, Pol 0 C 19 C 13, we obtain the total effective polarization as IKE2, Z, EE. Here, the subscripts R and I to the susceptibility stand for its real and imaginary parts, respectively. The above P00134110 Pol 14 analysis has been made for the highly doped regime, in which EM2, 222, while X 19B, C, describe the 0CP0, PE0, Pol, where steady-state optical response of the medium in the presence of a transverse magnetic field and govern the nonlinear wave. Z1, 22 IKE, 1. 1, 22 IKE, 1. Propagation through the medium. Now the real and imaginary. 1 1. E2. 2 E2. Parts of effective third-order susceptibility, 3 can EREI. In which 222 and 222 be employed to study dispersive characteristics and steady state. 11p 21p growth rate of the propagating modulated wave, respectively. It EQ 14 reveals that the total effective polarization PE can be observed from EQ 19b, that there is an intensity ER couples to the perturbed density waves at frequencies and dependent refractive index, via 3, leading to the polaron mode at frequency Pol ER. By algebraic simplification of EQ 14, the effective third-order polarization P 3 may be expressed as possibility of a focusing or defocusing effect of the propagation beam. EQ 19b reveals that the positive dispersive characteristic of the dissipative medium is possible at PE 2K2 E/M 242 Z 1 EE. As 3 becomes more positive, we may expect more P 3 P01234 E20 2 Pol 15 effective self-defocusing of the modulated polaron mode 0C 2. In order to obtain an expression for the threshold value of pump amplitude required for the onset of PL-LOP interaction K22E24 K22E2 3, where Z24222 and 2 E based amplification of modulated waves, we set E I0 and 220001P. Obtain E 220C 20. The transverse components of the oscillatory electron fluid velocity V0 in the presence of the pump and magnetostatic 0th plug E/M K20 fields obtained from EQ 3 may be expressed as we observed from above equation that the modulational instability of the polaron mode has a non-zero intensity V0x E 2I and V0y ECE0m 22 16. Threshold, even in the absence of damping. E0th, PL-LOP is found to have complex characteristics and is independent of effective E00C. Charge QS but strongly dependent on wave number K. 13.25, 12.00, 10.75, 9.50, 8.25, 7.00, 5.75, 4.50, 3.25, 2.00, 1 2 3 4 5 6 7 8 9 10. Wave number, K, A107M1. Fig 1, variation of, E0th, PL-LOP with K at C, P0. 13.25, 12.00, 10.75, 9.50, 8.25, 7.00, 5.75, 4.50, 3.25, 2.00, 1 2 3 4 5 6 7 8 9 10. Wave number, K, A107M1. Fig 1, variation of, E0th, PL-LOP with K at C, P0. Equilibrium carrier concentration N0, via P, through parameter. And the external DC magnetic field B0, via C. 6.1. 6.1. A10 Vm. A10 Vm. In order to express the possibility of PL-LOP interaction-based amplification of modulated waves in a weakly polar magnetoactive semiconductor plasmas, we employ the relation E K 21 3 ER 2 threshold pump amplitude E threshold pump amplitude E 0th PL-LOP 0th PL-LOP E0 21. Here, E is the effective nonlinear absorption coefficient. The nonlinear growth of the modulated signal is possible only if E obtainable from EQ 21 is negative. Thus, the growth rate of the modulated beam for pump amplitudes well above the threshold electric field can be obtained from X 19C and 21 as G plus B 2K3 E/M 222 242 Z 1E PQ Paul 124 E20 22 22 242 22 2 Paul 0 Paul 0 C 35.0 31.5 28.0 24.5 21.0 17.5 14.0 10.5 7.0 3.5 0.3 0.4 0.5 0.6 0.7 0.8 0.9 1.0 1.1 1.2 Cyclotron frequency / pump frequency, C/. Fig 2, variation of, E0th, PL-LOP with B0, via C/0, at P0. NK equals 2.7107 M1. 35.0. 31.5. 28.0. 24.5. 21.0. 17.5. 14.0. 10.5. 7.0. 3.5. 0.3 0.4 0.5 0.6 0.7 0.8 0.9 1.0 1.1 1.2 Cyclotron frequency / pump frequency, C/. Fig 2, variation of, E0th, PL-LOP with B0, via C/0, at P0. NK equals 2.7107 M1. 1 6 Threshold pump amplitude, E0th, PL lop A 10 Vm. Threshold pump amplitude, E0th, PL lop A 10 Vm. We observed from above equation that the growth rate, G, PL lop independent of its frequency, and instead, it depends on the frequency of the pump wave, 0, as well as lop mode, lop. Moreover, G, PL lop is found to be influenced by the wave number K, equilibrium carrier concentration N0, via P, through parameter, and the external DC magnetic field B0, via C. Results and discussion. In order to establish the validity of present model, we have chosen a weakly polar IIIV semiconductor plasma at 77 K as the medium. It is assumed to be irradiated by a 10.6 am, 0 equals 1.78 1014 S1, pulsed CO2 laser. Around this temperature, absorption coefficient of the sample is low around 10 am, and one may safely neglect contribution due to band-to-band transition mechanism. The physical constants involved are 26, m equals 0.014 m0, where m0 is the free electron mass, m equals 2.7 10 to 19 kilograms, n equals 1.48 1028 m3, qs equals 3.2 10 to 20 c, e equals 1011 s. 1, pH equals 10 to 2 s1, 1. Equals 17.72 and 15.68. This set of data is related to a typical n-InSb crystal. However, the results obtained in previous section may be applied to any IIIV semiconductor plasma. Using the physical constants, for n-InSb, given above, the nature of dependence of the threshold pump amplitude, E0th, PL lop for the onset of PL lop interaction-based amplification of modulated waves on different parameters such as wave number K, externally applied magnetic field B0, via electron-cyclotron frequency C, and doping concentration N0, via electron-plasma frequency P, may be studied from EQ 20. The results are plotted in Figs 1-3. Fig 1 shows the variation of E, with wave number K. Fig 2 shows the variation of E0th, PL lop with externally applied magnetic field B0, via C/0, at P0. It can be seen that E0th, PL lop is fairly independent on magnetic field when C0. An increase in the value of magnetic field causes sharp fall in E0th, PL lop. Around C0, E0th, PL lop attains a minimum value, for 106 Vm1 for n-InSb crystal when irradiated by CO2. 0th PL lop. Laser of frequency 1.78 1014 S1, corresponding magnetic field. At C, P0. It can be observed that E0th, PL lop is comparatively larger for lower magnitudes wave number. With increasing wave number magnitude, the threshold pump B0 equals 14.2 T. The occurrence of this minimum may be attributed to the fact that E0th, PL lop, 2 as evident from 0, C. Amplitude decreases parabolically. This behavior may be attributed to the fact that E0th, PL lop K1 is suggested from EQ 20. EQ 20. With further increase in the value of magnetic field causes sharp increase in E0th, PL lop, making it independent on magnetic field when C0. 50. 45. 40. 35. 30. 25. 20. 15. 10. 5. 0.10, 0.20, 0.30, 0.40, 0.50, 0.60, 0.70, 0.80, 0.9, 1.0. Plasma frequency/pump frequency, P/. Fig 3, variation of E0th, PL lop with N0, via P/0, at C0. Nk equals 2.7107 M1. 36. 33, 30, 27, 24, 21, 18, 15, 12, 9, 1 2 3 4 5 6 7 8 9 10. Wave number, K, A107M1. Fig 4, variation of, G, PL lop with K at C, P0 and E0 equals to 108 VM1. 50. 45. 40. 35. 30. 25. 20. 15. 10. 5. 0.10, 0.20, 0.30, 0.40, 0.50, 0.60, 0.70, 0.80, 0.9, 1.0. Plasma frequency / pump frequency, P/. Fig 3, variation of, E0th, PL lop with N0, via P/0, at C0. NK equals 2.7107 M1. 36. 33. 30. 27. 24. 21. 18. 15. 12. 9. 1 2 3 4 5 6 7 8 9 10. Wave number, K, A107M1. Fig 4, variation of, G, PL lop with K at C, P0 and E0 equals to 108 VM1. 45. 40. 35. 30. 25. 20. 15. 10. 5. 0. 0.30, 0.40, 0.50, 0.60, 0.70, 0.80, 0.91, 1.0, 1.1, 1.2. Cyclotron frequency / pump frequency, C/. Fig 5, variation of, G, PL lop with B0, via C/0, at P0. NK equals 2.7107 M1 and E0 equals to 108 VM1. 45. 40. 35. 30. 25. 20. 15. 10. 5. 0. 0.30, 0.40, 0.50, 0.60, 0.70, 0.80, 0.91, 1.0, 1.1, 1.2. Cyclotron frequency / pump frequency, C/. Fig 5, variation of, G, PL lop with B0, via C/0, at P0. NK equals 2.7107 M1 and E0 equals to 108 VM1. 61. 61. Threshold pump amplitude, E. Threshold pump amplitude, E. A10 VM. A10 VM. 0 THPL lop. 0 THPL lop. 51. 51. Growth rate, G. Growth rate, G. A10M. A10M. PL lop. PL lop. Fig 3 shows the variation of, E0th, PL lop with doping concentration N0, via P/0, at C0. It can be seen that, E0th, PL lop decreases with increasing doping concentration. 4. 1. 1. Growth rate, G, PL lop, A10M. Growth rate, G, PL lop, A10M. P0, the rate of decrease of threshold pump amplitude with respect to doping concentration is smaller, however, it increases with rise in doping concentration. Around P0. E0th, PL lop attains a minimum value, 5106 VM1 for n-InSb. 5. 5. Crystal when irradiated by CO2 laser of frequency 1.78 1014 s. 1. Corresponding doping concentration N0 equals 2.2 1024 M3. The occurrence of this minimum may be attributed to the fact that E0th, PL lop 01P. As evident from EQ 20. The doping concentrations for which the plasma frequency P exceeds the input pump frequency 0 have been not plotted in this figure because, in the regime when P0, the diffusion effects may pronounce and the theoretical formulation thereby needs a modification. Using the material parameters, for n-InSb, given above, the nature of dependence of growth rate, g, PL lop of modulation Li amplified wave on different parameters such as wave number k, externally applied magnetic field B0, via electron-cyclotron frequency C, doping concentration N0, via electron-plasma frequency P, and pump field amplitude 0, well above the threshold pump amplitude, may be studied from EQ 22. The results are plotted in Figs 4-7. Fig 4 shows the variation of G, PL lop with wave number k at C, P0 and E0 equals 2.5108 Vm1. The growth rate, G, PL lop has the usual characteristic dependence on the wave vector. 4. Small and nearly independent of externally applied magnetic field up to C equals 0.80. As the magnetic field increases, G, PL lop increases rapidly with an increase in the electron-cyclotron frequency, until it reaches its maximum at C0, and then lower magnitudes of wave number k, 6107. M1, G, PL lop decreases suddenly, and achieves its minimum at C equals 1.05 C. Shows a linear gradual increase with k, with further increasing the occurrence of the peak of G, PL lop around C0 may be the magnitude of wave number k, the growth rate, G, PL lop. Attributed to fact that G, PL lop 222, as evident from EQ 0C, increases quadrically. This variation of the temporal growth rate, G, PL lop with wave number k is in confirmation with the 22, the sudden fall of G, PL lop around C equals 1.050 may be attributed to increase in factor 2 in the denominator of usual dependence quoted above. 0C. Fig 5 shows the variation of G, PL lop with externally applied magnetic field B0, via C/0, at P0 and E0 equals 108 Vm1. It can be observed that initially, G, PL lop is very EQ 22. Prominent amplification characteristics reveal that no growth rate could be achieved beyond C equals 1.050 because in this regime of magnetic field the phenomenon of cyclotron absorption may dominate the instability process and hence the 45, 40, 35, 30, 25, 20, 15, 10, 5, 0, 45, 40, 35, 30, 25, 20, 15, 10, 5, 0, 1 2 3 4 5 6 7 8 9 10, 1 2 3 4 5 6 7 8 9 10, 8, 8, 0. Fig 7, variation of G, PL lop with E0 at C, P0 and K equals 2.7107 M1. 0. Fig 7, variation of G, PL lop with E0 at C, P0 and K equals 2.7107 M1. 5A106. 106. 5A105. 105. 5A104. 104. 5A103. 103. 5A102. 0.10.20.30.50.60.70.80.91.0. Plasma frequency/pump frequency, P/. Fig 6, variation of G, PL lop with N0, via P/0, at C0. Nk equals 2.7 107 m1 and E0 equals 2 108 vm1. 5A106. 106. 5A105. 105. 5A104. 104. 5A103. 103. 5A102. 0.10.20.30.30.40.50.60.70.80.90. Plasma frequency/pump frequency, P/. Fig. 6, variation of G, PL lop with N0, via P/0, at C0. Nk equals 2.7 107 m1 and E0 equals 2 108 vm1. Pump field amplitude, E, A10 vm. Pump field amplitude, E, A10 vm. 1. 1. 1. 1. 5. 5. 1. 1. Growth rate, G, PL lop, A10m. Growth rate, G, PL lop, A10m. Growth rate, G. Growth rate, G. M. M. PL lop. PL lop. Growth rate of PL lop interaction-based modulation ally amplified wave vanishes. Washing out of growth rate at and above C equals 1.050 provides a favorable range of magnetic field which becomes more and more confined with increasing pump field amplitudes. The above said variation of growth rate may very easily be utilized in the construction of optical switches. High, 106 m1. Hence, G, PL lop strongly depends on electron density of the semiconductor plasma. The nature of the G, PL lop P graph is similar to conclusions arrived at by Salimullah and Singh 27, who considered the interaction of an extraordinary mode subjected to perturbations parallel to the magnetic field. Thus higher growth rate of modulation ally amplified wave can be attained by increasing the doping concentration of the medium by n-type doping in the crystal. However, the doping should not exceed the limit for which the plasma frequency P exceeds the input pump frequency 0, because, in the regime when P0, the electromagnetic pump wave will be reflected back by the intervening medium. It may be thereby concluded that semiconductor plasmas are the most appropriate hosts for modulational instability processes. The preceding analysis has been performed for IIIV semiconductor plasmas like n-InSb with doping concentrations approaching critical density, i.e. doping concentrations for which the corresponding electron-plasma frequency is comparable to the incident pump frequency P0. Doping concentrations of such high magnitudes are quite relevant to semiconductors of the IIIV group 28 and have been extensively employed by several workers to study their various characteristics. 29. Fig. 7 shows the variation of G, PL lop with pump field amplitude E0 at C, P0. It can be observed from this figure that G, PL lop increases sharply with E0, achieving a peak at E0 equals 3 108 vm1. Beyond this value of pump field amplitude, G, PL lop decreases parabolically with pump field amplitude. Thus, by suitably choosing the pump field amplitude, maximum growth rate of PL lop interaction-based modulation ally amplified wave can be obtained in a semiconductor plasma. Conclusions. In the present study, a detailed numerical analysis of the threshold pump field for the onset of PL lop interaction-based amplification of modulated waves and growth rate of modulated wave well above the threshold pump amplitude in magnetoactive semiconductor plasmas have been undertaken. The analysis enables us to draw following conclusions. The hydrodynamic model of semiconductor plasma has been successfully applied to study the influence of different parameters such as externally applied magnetostatic field, doping concentration etc. on threshold pump amplitude and growth rate of modulated wave, well above the threshold pump amplitude, in magnetoactive semiconductor plasmas duly shined by slightly off-resonant not too high power pulsed lasers. The threshold pump amplitude for the onset of PL lop interaction-based amplification of modulated waves decreases with increasing the wave number amplitudes. The presence of an external transverse. Fig 6 shows the variation of G, PL-LOP. With doping 8-1. DC magnetic field, for which electron-cyclotron frequency pump wave frequency, and high values. Concentration N0, via P/0, at C0 and E0 equals 2.510 Vm. Vm1. It can be observed that G, PL-LOP is very small, 102 M1, for low doping concentrations, P0.1 C, corresponding N0 equals 2.21022 M3. It increases linearly with rise in electron density of the semiconductor plasma. At high doping concentrations, P0, corresponding N0 equals 2.21024 M3, G, PL-LOP is very of doping concentrations, for which electron-plasma frequency pump wave frequency, effectively reduces the threshold pump amplitude required for inciting the amplification of modulated waves. The growth rate of modulation ally amplified wave is found to increase with wave number of LOP mode. The presence of an external transverse DC magnetic field, for which electron-cyclotron frequency pump wave frequency, effectively enhances the growth rate of modulation ally amplified wave. High levels of doping concentration are favorable to large growth rate. The increment in pump field amplitude increases the growth rate of PL-LOP interaction-based modulation ally amplified wave, resulting in peak at E0 equals 3108 Vm1. Acknowledgement. The authors are thankful to Dr. Manjeet Singh, Department of Physics, Government PG Nehru College, IJERT, Haryana, for his kind cooperation.